welcome to another video. In this one I'm going to explain how we can estimate the result of differential equations using Taylor series. So before we do that, just think about why would we want to use Taylor series here? Why would we go for Taylor series in these situations? And well, here's the answer. I mean, think of what we always have. We have initial values. So we have, for this value of x, this is the value of y. Great. And we also have an equation to calculate the derivative, right? We have an equation that gives us the gradient. So if you're thinking about it, if you have your Taylor series here, right? If you have y equals f of x, and instead of y, I'm putting f of x here, and I put that in my notation, which, could be said that it's different. So I say that y, the function, so y is going to be equal to the value of the function in general is going to be equal to y for that initial value plus the derivative at that initial value, and then x minus that initial value of x, and this is just really the same thing as here, right? And here I can put a value of x and say, well, what happens if x is equal to 8 or 9 or minus 1, and it will estimate the value using the Taylor series. So this is just the same notation as before. Well, with this values here and this thing here, if you think about it, I have this and I have this. And all I have to do is substitute using these to get these ones, and using the result of the differential equation to get this one. So I get the two first elements really quickly. Normally just in the question itself, just very quick substitution. Now this ones might be tougher to get, but I'm going to show you how. And now if I can do that, if I can get like further elements, if you can get further terms of the Taylor series, and I know that the value is close enough, that this is going to be a good way to estimate. So that's what we're going to be doing today. So in order to take further derivatives, all you have to do is take the differential equation, take the derivative of that, and it's going to give you the second derivative. And if you take the derivative of that result, it'll give you the third derivative, and so on. So let's do an example straight away. So they're asking me to find a Taylor polynomial to approximate the solution for x equals 0.2. And in this differential equation, y squared minus xy. And I know that when x equals 0, y is equal to minus 1. So, and it's specified, so just use 4 terms in the polynomial. Again, I have to construct my Taylor polynomial. Now, I have the first values, and I have the derivative. We can just do it very quickly just by substituting, so I get that it's going to be 1. So this one I already have. Now, to calculate the second derivative, I'm going to have to make the derivative of this thing here, right? Now, when I make the derivative of this thing here, what I'm going to get is something quite big. Now here on this side, clearly I get just a second derivative, same thing as y prime prime, if you will, same thing as here. But on this side, it's going to be something longer. And be careful because there's a lot of implicit differentiation going on here. So I get this part here, simply I get 2y, which is the derivative, times y squared. Remember that I did implicit differentiation, which is just like using the chain rule, minus, and then product rule. So, right, this is the x is gone here, and the y becomes a 1 and times y prime. And this thing here becomes this expression, but we're not done yet because we have this expression that has the gradients in it. And you could go ahead and substitute, but we're going to get rid of these ones by using these ones. So the second derivative, I just substitute, and I end up with this expression here, just by operating. So that's the value of the second derivative. And yes, that was a bit of hard work, but you have to know how to do this. So I can substitute now and put the 0, because that's the term I'm going to base it all on. And I'm going to find a solution for it, and it's going to be minus 1. So that's how I calculate this term here. And I can calculate the third derivative too by doing the same thing. So I get that's going to be 2. Now what I have by doing this is I have this term given to me in the initial conditions, this term given to me by substituting in the differential equation itself, this term, which I obtained by taking the derivative of the differential equation, and that would give me the second derivative, and then substituting, and this term which was done the same way. Now I can build the Taylor polynomial. This is what I need to construct. So I just substitute with these values, and I get the Taylor polynomial. Now, because I've already truncated it, I'm going to put an approximation sign. And hence I can solve x minus 0 is just going to give me x squared. This actually would be kind of more a Maclaurin polynomial. And I can substitute now, put the x to be 0.2, and hence I get the final values. And this will be my estimated result. And that's how you estimate solutions to differential equations using Taylor polynomials. Really just as simple as that. If you have been watching since the beginning, this is the end really, because we have no further things to add for the whole syllabus. This is really where it ends. This is the end of the option. Now, before we leave very quickly, I just want to say that mathematics is always more stuff. There's always people who've taken every little thing a little bit further. And if you're interested in it, I do encourage it. It's always kind of interesting to read. Slow, but interesting. And examples are like many more different ways of solving differential equations, many applications to differential equations. The whole big world expands there. And in general, all the fields you have studied, there's going to be a lot more math to find out there. Finally, I have to say many fields that you haven't even started with, things like discrete mathematics, number theory, stuff that I love a lot. Actually, I think it's really beautiful. Some of my favorite stuff. But bottom line, last thing I want to say, of course, as usual, to be honest with you, thank you for watching. Okay, I'll see you in class. Bye.